Washer method is different than the disk method because there is a hole in the center, hence the difference between a washer and a disk. Okay, now just like area between the curves, between two curves, we have to follow that same method for washer method. Okay, disk method, there was not any space between area to be revolved and the axis of revolution. Okay, but now there's going to be a space, so we just have to subtract out that empty space, and that's all we have to do. Okay, now before we get to that shaded blue box, what I want to do is kind of write things in the form before we see that. If we revolve this figure around this axis, it'll trace out this figure right here, correct? Okay, but for us, we're going to see some function looks like this from like A to B. Now, since this function is not touching the axis of revolution, there's this hole created when you revolve something. So you got to think about the area between two curves. Now, what I like to do first before we get to this is I like to break it apart. If we revolve the big radius around, just like we would for disk method, it would be pi antiderivative A to B. Big radius squared, right? And dx minus, we got to subtract out this volume, right? Pi A to B little r, and I'll call it r of x squared dx. So all we're doing is taking the outside radius like we normally would and subtracting out that inside radius, the inside part to be that would create that hole. And knowing what we know about integrals, we're going from A to B on both, so we can make this a difference inside the integrand, like so. So this would be our formula for the washer method for solids of revolution. Now, this is the formula we would use if the axis was axis of revolution is the x-axis. If this changes, we have to actually figure out what capital R is and lowercase r is. And we might have to do like axis of revolution minus curve. Okay, we might have to do curve minus axis of revolution to get whatever that radius is. Again, this is for axis of revolution x-axis, because r of x would be the height off of the x-axis, and lowercase r of x would be the height off of the x-axis. Okay? Questions on this so far? I think it's pretty easy. This would be a figure that we maybe make. I think you guys see this one. Is this number 4 in your guys' packet? I believe 7.2. It's 3 or 4. I remember that. And that gets revolved around an axis. If this was the x-axis, we're revolving around, it'd just be capital R squared minus lowercase r squared. These would just be different figures that we can model. If we went around the y-axis, obviously everything would be in terms of y. Okay, let's do a problem. I'll find the volume of the solid formed by revolving the region bound by the graphs of f of x equals square root x and y equals x squared. And that they could call that g of x equals x squared. And we're revolving about the x-axis. So this would be one of the easier forms, probably the easiest form of doing this, the washer method. Do you guys know the boundaries yet, just by looking at the two functions without setting them equal to each other? What number is the same if you square it or square root it? 0 and 1. Yeah, both of them. So they'll be your bounds. We could just set these two equal to each other, right? Or sometimes you see the pattern. Okay, so we're going from 0 to 1, and we'll see this graphically also. So again, would you like to graph these? I'll make you guys graph them on our worksheets. Okay, square root x. Okay, we're at 0, 0. If we let x equals 1, then y equals 1. If x is, I'm not going to go 2 because that would be a decimal, right? So we can go to 4. And then 2. So right here for square root x. And then y equals x squared. And a lot of times I like to label these so I know which one would be the top function, bottom function. We'd have 0, 0, right? 1, 1 again, and then maybe 2, 4, so that'd be way up here. So this would be the area that's going to be revolved around the x-axis. Now on your worksheet, it'd be really nice if you guys drew this little circle arrow so you know what you're revolving around. It's going to be a totally different problem if we're revolving around the x-axis versus the y-axis, right? All right, we know the area, using the washer method, if we revolve this, it would create this solid, right, with this empty space in the middle, okay? And so we definitely have to subtract out that empty space, so this would definitely be the washer method, okay? Washer method, remember, would be pi a to b. Now I'm going to do this once, top radius, or top curve, squared minus bottom curve, squared, and then dx, right? Top curve, f of x. So a to b. Actually, let's put the values in. That'd be what, 0 and 1? 0 to 1. Top curve is f of x, so it'll be square root x quantity squared. Minus bottom curve, which would be x squared. Squared dx. All right, let's try and do this on a calculator, then we'll check using calculator, that's fine. I would definitely simplify before we integrate. Do a rewrite. Square root x squared, that'd be x, minus x to the fourth. Oh, this is piece of cake. Watch now we make a mistake. Okay, what do we got here? 1/2 x squared, is that right? 1/5 x to the fifth. Evaluated 0 to 1. Oh, I like the 0, 1. That's nice. That's not too bad either. Pi. 1 squared would be 1 times half would be half. 1 to the fifth is 1 times a fifth. 1 to the fifth, yeah, times a fifth, minus a fifth. And then minus 0, right? Don't need to write it. Common denominator, tenths. This would be 5/10 minus 2/10 would be 3/10. 3/10 pi. And then units would be units cubed. Let's switch to black pen. Or red, doesn't really matter. And let's revolve this bad boy around the y-axis. Okay? Same question. Revolve around the y-axis now, kind of like your guys' worksheets, right? Okay, good news is this is not too bad because the axis of revolution is the y-axis, and we're just going to go top curve and then bottom curve. Now, since we're revolving around a vertical axis, we have to write our equations x in terms of y, correct? So let's start off by doing that. So I'm going to say y equals square root x, and then solving for x, square both sides, x equals y squared, right? All right, now we take the other one, solve for x, y equals x squared, square root both sides, x equals square root y. And it would be plus or minus square root, wouldn't it? We're only going to take the positive value over on this side, quadrant 1. Okay? So sometimes when you're taking the square root of both sides, you have to plus or minus. You got to figure out which one you need. Do you need this one or do you need this one over here? Okay, obviously I want this one. So we create this bounded region still. Okay, what would the boundaries be in terms of the y-axis? Looks like still 0 and 1, right? That's nice. Okay, which one is the top curve this time? Okay, it's this one, right? Which was y equals x squared, right? Which turned into x equals square root x, or y equals square root y. That should be y, shouldn't it? X equals square root y. Okay, so that'd be our top curve. So pi, antiderivative, 0 to 1, top curve, which is that distance, x equals square root y, so square root y, quantity squared, minus bottom curve, which came from f of x, which is y squared. Do you guys notice anything kind of nice about this problem? It's dy this time also. Anybody notice anything kind of nice? It's the exact same, right? That happens sometimes. 0 to 1, that'd be y minus y to the fourth, dy. And we can just jump right to that 3 pi over 10, right? We should find the antiderivative, then go from there, but I think we need to practice more on solving for x instead of our antiderivative. I think we're good after that. Okay, questions on this? All right, let's revolve this. Same question. Let's revolve this around another axis. How about, let me erase all of this. Anybody have a favorite axis they want to revolve this around? No. There's 2 dimensions, guys. Save that for college. What? We already did that. Y equals 4? All right. Is that on your guys' homework at all? Something pretty close to that? I mean, we could do the same thing, but let's just, since it fits on my graph, let's go y equals 2. So this will be our axis of revolution now. Y equals 2. Let's just kind of see what happens. Okay. Since our axis of revolution is above the curves, we kind of have to go up to the curve and then back down to create this distance, right? To this radius right here that we need. Correct? And then we need this radius right here. Correct? Okay. So it's going to create a washer. It's just going to have a bigger opening in the center. The area, the volume should be bigger than 3 pi over 10, right? Because you're sweeping out a bigger space, right? Let's see what we can get here. We know we're still going from 0 to 1, okay? But we need to figure out what big R is, which is the outer radius. Okay, and that's going to be the distance from the axis of revolution to this curve. So how do we figure that out? Capital R we'll call the outer radius. That's the distance from here to here. Well, what do? We go to green pen and we say, okay, to get this distance, I need to take this distance minus this distance will give me the radius, correct? Okay, so the distance from the x-axis to the axis of revolution, which is y equals 2. So I need to go 2 minus the height of the bottom curve. Now this is where it's a little bit confusing because you say, well, it's top curve minus bottom curve. Well, it's big radius minus small radius, especially when the axis of revolution is above the area to be revolved. Okay, big radius minus small radius. Okay. And think about it, guys. If we revolve this curve right here would be on top, right? So that would be the top curve, honestly. Okay. But I don't want to make you guys transform this till it's up here, reflect it, and shift it up. We don't want to do that right now. Okay. So this is much easier. So 2 axis of revolution minus this curve, which was y equals x squared. Okay. And then our little radius, r, that creates that volume to be subtracted out, would be, let's see here, the distance from the axis of revolution to f of x, right? You take 2 minus this much to get that inner radius. So 2 minus, what would that be? Square root x? Okay, now let's use our formula. Pi from 0 to 1, outer radius, 2 minus x squared, squared, minus inner radius 2 minus square root x squared dx. Okay, just use your calculator in this, guys, because we would have to multiply this all out, combine like terms. It'll be a nice polynomial, basically. We would have a half power on one of our factors. Use your calculator real quick and figure out what the approximate volume would be. Check with your neighbor, please. Does it help that I wrote out the big radius and the little radius separate before I put them into the function, into the formula, I should say? You guys got something? Pi? Ooh, we still got pi in there. Good. So we had 3/10 pi before, and now we have over 1 pi. All right, so we have this one. We figured out the outer radius and the inner radius. And we're using, it's called the washer method because we have that void that we need to subtract out. Some people call it the donut method because it creates a donut with a hole in the middle, but whatever. Okay. Same problem, different axis of revolution. I'm going to clean this up real quick. X equals 1? Oh my goodness. Get out. X equals 1? Why x equals 1? So if we have this, let's do this. Let's go y equals -1 as our axis of revolution. And why am I doing that? Because now the axis of revolution is below the curve. What? No, because it's going to be volume. You'll see why. It's still going to be positive. Okay, axis of revolution is the line y equals -1. Now, our whole goal, guys, is to figure out what's the upper radius, what's the inner radius, right? Outer radius, inner radius, okay? Since we are revolving around the line y equals -1, which is below the curves, it's usually nicer for us. We got to figure out what is this radius right here, and then what is this radius right here, okay? All right. Capital R for this situation. Well, it would be this radius added to this radius, but it's actually, okay, what would that be? F of x, which would be square root x, minus -2, which creates square root x plus 2. So we, minus -1, my bad. I was thinking putting at -2 earlier before we started the question. There we go. So we're essentially adding 1 to our radius. Okay. So when the axis of revolution is below the area to be revolved in washer method, that's going to be outer curve minus axis of revolution. Outer curve minus axis of revolution. And then for lowercase r, then inner radius would be curve, which would be x squared, minus axis of revolution. In this case, because axis of revolution is in the negative land, we'd have x squared plus 1 then to increase that length by 1. Okay, the hardest part, I think, is coming up with capital R and lowercase r. So let's use your calculator on this one after we have it written out. We'd have pi 0 to 1, and then the outer radius would be square root x plus 1 squared minus x squared plus 1 squared, and then dx. Make sure you have brackets around the whole thing. And then check with somebody, please. I wonder if this is going to be less than 1 or more than 1. What are you guys getting? 667. We'll truncate right there. pi than units cubed. All right. So it's going to be a little bit less than when the radius was 2 units above. Any questions on this? Pretty easy. All right. Do you think you guys can do some problems in your worksheet now with this stuff? Not too bad. Okay. Do you want to look at one more in terms of y? Y-axis, axis revolution. How about this? Let's do the setup on the next one real quick. Let's do the setup. Find the volume of the solid formed by revolving the region bound by the graphs of y equals x squared plus 1. Okay, right side up quadratic, shifted up 1 unit. Y equals 0, x equals 0, and x equals 1. So they're creating this region that's bound by these different equations. We're spinning it about the y-axis. Okay. Spinning about the x-axis would have been really easy. That'd be a disk method problem, right? But because this function is not touching the entire y-axis, we have this hole created. Okay, and now it's going to be part disk method, part washer method. Okay, now we need to break this up into 2 integrals. Okay, they did something nice for us. They already solved these in terms of x. They called it r. I just call them x right now. Okay. So if we have the situation, we need to break this up because we have different upper and lower curves. Okay. So for here, from 0 to 1, 0 to 1, we just have the value 1, don't we? That's it. So we could say 1 squared minus 0 squared, right? But this is just a disk method problem, and we have a radius of 1, so outer radius for this section, capital R, equals 1. That's it. So 1 squared dy. Plus, let's figure out from 1 to 2. Outer radius, still 1. Inner radius, that'd be x equals square root y minus 1, right? All right, so it'd be outer radius minus inner radius. And then dy, obviously. This problem's not too bad. That'll just be pi times y from 0 to 1, right? You square this. That'd be y minus 1. Then take the opposites. Negative y plus 2, or 2 minus y, times pi. Take the antiderivative from 1 to 2. Not too bad. Check to see if you guys get this answer when you antiderive this or use your calculator. I got 3 pi over 2 units cubed. See if you guys get that. This should be an easy problem without a calculator. You guys getting 3 over 2 pi? That'd be 1 plus a half, 3/2. All right, what I did right there, that's how quick you guys should be able to do those problems. Go through, find your radiuses, and then set up your integral and go through. Do your integration pretty quickly, and then calculator problems, set up your integral, then use your calculator. Okay?